Welcome back, everyone. We're going to continue our discussion on transformations between coordinates. Specifically, we will talk about basis transformation between coordinates. We said that unlike the transformations of the actual coordinates themselves, the basis transformations between coordinates are linear. Right, and this comes from the orthonormality of the basis vectors. So if we draw our trusty diagram again, so let me go here and draw my diagram. So I have my Cartesian system, Cartesian basis, x hat, y hat, z hat, and then we said that we want to go from the Cartesian to the cylindrical. So I have my cylindrical basis here, which is r hat, phi hat, z hat. We said this transformation is linear, and we can write it as m. By linear, we mean that we can write it as a, let me get the m right. Okay, by linear, I mean we can write it as a, of course, whenever you have a linear transformation, you can write it as a matrix equation from linear algebra, hence the name linear algebra. So I can write the result, which is the destination, which is r hat, phi hat, z hat as a vector, as one of those column vectors from linear algebra. I don't mean my directed segment or line vectors from EM. I'm talking about from 3D space. I'm talking about a vector in the real linear algebra sense. Anyway, just a column thing, a column here. So this can be written as m times x hat, y hat, z hat. So this is how you encode that transformation. And you can encode it this way only because this transformation is linear. We will write it down exactly in a bit. But this is what the transformation would look like. The advantage of writing it this way is that now going back is easy. Going back is simply a matter of multiplying r hat, phi hat, z hat by m inverse. So to go in one direction, it's m. To go in the opposite direction, it's m inverse. Same thing, we can go from the Cartesian to spherical coordinates. So spherical basis, we have r hat, theta hat, phi hat, and transformation is n, meaning I can write r hat, theta hat, phi hat as n times x hat, y hat, z hat, where n is a matrix. And again, this gives us the ability to go back n inverse. Now this gives us, once we know the transformation from Cartesian to cylindrical and Cartesian to spherical and its inverse, from the nice properties of linear algebra, we already for free now have the transformation from cylindrical basis to spherical basis and the transformation from spherical to cylindrical. Right? Why? Because, you know, we could go this way. If we want to go from cylindrical to spherical, I could first go in this direction. Right? Go from cylindrical to Cartesian and then go from Cartesian back to spherical. I can do two transformations to get an equivalent transformation from cylindrical to spherical. So I go from cylindrical to Cartesian first, and then I go from Cartesian to spherical. So going from cylindrical to Cartesian, that's an m inverse. I first multiply by m inverse, and then after I get the result, I multiply by n. It comes to the left. Right? Meaning that so I'm going towards spherical. So r hat, theta hat, phi hat should equal. So I'm starting at cylindrical, r, phi, z. I first go to Cartesian basis, meaning I go opposite direction, I multiply by m inverse. And then the result is in the Cartesian basis, but I want to jump now from the Cartesian back to the spherical, so I need to transform by n. So I multiply to the left by n. Right? And then the inverse is simply, this is another property of matrix algebra. If you take two matrices and you take the inverse, so first you transpose the matrix, you swap the matrices, so, and then you invert. So this is, let me write down the property here. A, B, where A and B are matrices, inverse is just B inverse times A inverse. This is a basic result in linear algebra. So this I can write as M inverse inverse, which is M, and then N inverse. So going back is just M, N inverse. Right. The idea is that you only need to figure out two transformations. The one from Cartesian to cylindrical and the one from Cartesian to spherical, and that gives you for free all inverse transformations and transformations between the cylindrical and the spherical bases. Okay, simple enough, but let's figure out what M. So we need, our job now is to figure out what are the M and N matrices. Let's do that right now. So what is the M matrix? M matrix is a transformation from the Cartesian basis into the cylindrical basis. So we have our 3D space, and we have a specific point in the 3D space, P, call it point P. And that point is going to have, you know, three bases, depending on what coordinate system you have. Let's say you have your origin here. Oh, by the way, one subtle point I have to remind you of is here we are dealing with three coordinate systems that all share the same origin. If the origin is different, then the transformations will be a little bit different. But we don't need to worry about that. It's very uncommon for us to have to worry about changing the origin of the coordinate systems. Typically we pick an origin and we stick with it. So, but I mean, forget about the origin. What I'm trying to say. Just label a point in space, and this point in space is labeled, has an address that depends on our coordinate system. And depending on what coordinate system we choose, there are going to be different bases at that point that we can use to decompose any vector at that point. So let's write down the start bases and the end bases that we want to transform to with different colors. So so I want to do cylindrical. So let me start with so the end now is going to be R hat, phi hat, z hat, and the start is going to be x hat, y hat, z hat. I want to transform using some kind of matrix, transform x, y hat, z hat to r hat, phi hat, z hat. In other words, I want to write r hat as a linear combination of x hat, y hat, z hat. I want to write phi hat as a linear combination of x hat, y hat, z hat. And finally, I want to write z hat as a linear combination of x hat, y hat, z hat. The last one is really simple. What is z hat as a linear combination of x hat, y hat, z hat? It's just 0, 0, 1, right? Because, you know, z hat equals z hat. That's it. The final one, the final basis vector is common to both coordinate systems. We are left now with r hat and phi hat. So let's assume we are looking here in space. So this page here I'm writing on is a two-dimensional page, right? But space is 3D, so I can change my orientation. I can look at three-dimensional space from any direction. So let's assume I'm looking at the top, from the top. So I'm looking such that the z-axis is pointing towards me. So the x-axis and the y-axis are going to be on the plane of the sheet of paper I'm writing on. So my let me write my origin in green, I guess. So my x hat will be pointing in this direction. my y hat is going to be pointing in this direction. My z hat is going to be pointing outside the page. Now I want to start with r hat. I want to write r hat in terms of x and y and z. R hat is going to be something like this. Right? So it's going to be, so why is it in this direction? Because let's say at this point, this is where the r coordinate, small r coordinate is increasing. So it's going to be pointing towards where the coordinate is increasing. It's going to have unity magnitude. So the angle, of course, is going to be the coordinate phi. So how do I write r hat in terms of x and y? Well, I just have to decompose it. I just have to first project it on x hat. So this is going to be cosine phi x hat. That's going to be its x hat component. And then I find its projection on y hat, simply enough. The projection from geometry, the projection is going to be sine phi y hat. And then the projection on z hat is 0, because z hat is perpendicular to r hat. So there won't be any z hat. Okay? So we found now the first row. The first row is cosine phi, sine phi, 0. Now I want to project phi hat. Where is phi hat, by the way? Phi hat is in the direction of increase of phi. And that direction at that point is going to be here, right? Because in the cylindrical coordinate system, phi increases in that direction, right? So this is going to be phi hat. This basis is orthonormal, so phi hat is going to be perpendicular to r hat. So phi hat and r hat are going to be perpendicular always to each other. If we shift r hat by phi, phi hat is going to be shifted from y by the same phi. So this angle is also going to be phi. I extend the line backwards here. All right. So phi hat projects on minus x hat, because phi hat projects here, right? And then it projects on y hat. So I'm going to have, when I write the projection of phi hat on x hat, it's going to be projected on minus x hat. And it's going to be sine phi, because the sign is here. The sign is here. So it's going to be minus sine phi x hat. And then projection of phi hat on y hat is simple. It's going to be cosine phi y hat. So the transformation here is going to be minus sine phi cosine phi 0. And that's it. That's M. That is M, right? So M is this matrix. We found M. And then M inverse is simple. M inverse is from linear algebra. So you have to review linear algebra for this. You can either do cofactors and use the determinant, or you can find M inverse by inspection. So by inspection, you can say, hey, M inverse is just so what is M inverse really? So this is M inverse. M inverse is the opposite transformation. So we end up at x hat, y hat, z hat, and we start at r hat, phi hat, z hat, and that transformation is going to be cosine phi minus sine phi 0, sine phi cosine phi 0, 0, 0, 1. And you can inspect that this is correct, right? If I multiply M inverse by M, I'll get the identity matrix. And you can see that cosine phi times cosine phi is going to be cosine squared. Minus sine phi times minus sine phi is going to be sine squared. Cosine squared plus sine squared is 1. So you get 1. And then you multiply then the first row with the second column. Cosine sine, cosine times sine. And then minus sine times cosine is going to be cosine sine. It's going to be sine cosine minus sine cosine is going to be 0. And then you multiply the first row by the third column. So it's going to multiply by 0 here. Cosine by 0, sine minus sine by 0. And then 0 by 1 is going to be 0. Same. So if you do this multiplication, you'll end up with 0, 1, 0, and 0, 0, 1. You can check that. You will get the identity matrix. So this matrix is an inverse of that matrix. Notice something interesting about it. M inverse is not just the inverse of M, it's also the transpose of M. So M inverse equals M transpose. What do you mean by transpose? By transpose, we mean take any row and turn it into a column. So you see here I had cosine, sine 0, and I becomes a column here, cosine, sine 0. Minus sine, cosine 0, it's a row, it becomes, the second row becomes the second column here. Minus sine, cosine phi 0. 0, 0, 1, the third row becomes the third column, 0, 0, 1. This is a property of orthonormal vectors. Bases. Because the bases are orthonormal, the inverses of the transformation are just going to be the transposes. So this simplifies also finding the inverse. You know that the bases are orthonormal, therefore the inverse is simply an act of finding the transpose. All right, so this is the M matrix. We found it. We found both the M and the M inverse matrix. And now we want to find the N matrix. Let's do that next. Let's move towards the other transformation we want to find, which is the transformation that goes from Cartesian to spherical, the N transformation. So essentially, what I want to find is starting with Cartesian, x hat, y hat, z hat. Those are the Cartesian basis vectors. I want to multiply it by some transformation n such that I get the spherical basis vectors r, theta hat, phi hat. Okay, so to help me find this transformation, let me draw some diagrams. And again, I'll use the convention of the origin being in green and the end being the end point being in the end point of the transformation being in red. And I want to again, and because this is 3D space, I cannot easily draw 3D space on the sheet of paper. I want to change my perspective. I want to look from different perspectives. So first, let me look from the perspective of the xy plane, right? So let me assume that I'm looking above so that the z hat vector is pointing outside the paper, and let me draw the x hat vector and the y hat vector. Now, where would the big R hat vector be? The big R hat vector will be something that's pointing outside the page in an angle, right? Let's say R hat increases in this direction. So this R hat is not on the page. This is something that's pointing at an angle outside the page, right? Because from the origin, this is spherical, right? The origin is here, and this is tuck, 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 and pointing out. So this is not on the plane, not on XY plane. It's hard to draw on 3D, but this is what it is. However, the projection of R hat, R capital hat, is on the XY plane. So, right. So to help you see this, let me draw two perspectives. So this is the perspective where z hat is going. I write it as a dot, meaning z hat is going outside the page, and then I could write it from another perspective where x hat is leaving the page towards me. So in this case, I'm going to have y hat here and z hat. So here I'm simply in the first perspective, I'm looking at the xy plane from above. In the second perspective, I'm looking at the y hat z hat plane from the side. So from the on the y z hat plane, right? Let me draw it also here so that perhaps it's going to be helpful to draw it for a point here, P, O. So P, this is P. So this is, let's say, X. Let me attempt to draw it as a three-dimensional image, right? So Z hat will be going to be something like this, R hat. And it's going to be an angle theta with respect to Z. And its projection is going to be an angle, on the XY plane is going to be an angle phi with respect to X hat. So this is just its projection on the XY plane. Okay. So looking at it from this perspective, this R here is going to have a projection on the Y hat Z hat plane. But either way, right? So let me simplify. So I want to write R hat in terms of X, Y, Z. So first, to write R hat in terms of X hat, first I want to take this R hat and project it on the XY plane. That's the first step I need to do. So how do you project it on the XY plane? You just multiply by sine theta, right? So this is R hat. Cosine theta is the projection on the Z axis, Z hat line. R hat sine theta is the projection on the XY plane, right? So the projection here is going to be sine theta, right? R hat, of course, has magnitude 1, right? But then this sine theta, so the first you project on the XY plane, X hat, Y hat plane, and then after you do the first projection, you do a second projection. So this is the first projection, and then you do a second projection towards towards X hat. The second projection is simply this, because this is phi, is simply going to be cosine phi. So this is going to be sine theta. Let me go back to black. Cosine phi X hat. Right? Simple. I had to do two projections. All you need to do here is try to imagine things in 3D. So looking at this diagram, I first did a first projection of R hat into the XY plane, and then I did a second projection into the X hat line. The first projection is just sine theta. The second projection is cosine phi. And then now I want to find the component on the Y hat line, right? And that's simple. It's the same projection on the Y hat XY plane, which is sine theta. But now the projection on the Y hat line is just going to be now sine phi. So it's going to be sine theta, sine phi, Y hat. And finally, the projection of R into Z hat is just going to be, I'm projecting it this way, is going to be just cosine theta. So plus cosine theta Z. So the transformation is as follows. The first row of the transformation is as follows. From geometrical considerations, sine theta, cosine phi, sine theta, meaning expand, sine phi, cosine theta. So all of this is from geometrical considerations and projections in 3D space. That's all it is. The next step now is right decomposing phi hat. Okay, phi hat is always going to be 90 degrees. Sorry, theta hat, not phi hat. So here in the 3D image, where would phi hat be? Let me draw it here actually. Well, first you have to the angle between. So let me actually draw it here like this. So this is going to be x hat, y hat, z hat. If r hat was pointing in that direction, phi hat, again, this is three-dimensional space, is going to be 90 degrees. Right? So this is going to be theta hat, sorry, theta hat, not phi hat. Imagine this is pointing downwards with respect to the xy plane, right? And this makes sense, you know, the theta coordinate is decreasing in that direction. So the first step is we need to project this on the xy plane. What is the angle here? The angle here is theta. So the angle between phi hat and the xy plane is theta, right? Because of the symmetry, r hat and theta hat should be always 90 degrees with respect between them. So first, same thing, it's two projections. We have first to project towards the xy plane, and then take this projection towards the x line, and again take it towards the y line. So so theta hat is going to be first a projection towards the xy plane. So it's going to be cosine theta, and then a projection towards this is phi, towards the x hat line is going to be cosine phi, x hat, and then the same projection towards the xy plane, cosine theta, and then now we project toward the y hat line, so this is going to be sine phi, and then finally we need to project towards the z-axis. The z-axis extends downwards, so the projection goes towards the negative of the z hat line. So this is going to be, and it's of course it's going to be a sine, because this is projection towards the xy plane is cosine, projection towards the normal to the xy plane is sine from geometrical considerations. So this is going to be minus sine z hat. So the second row is going to be cosine theta, cosine phi, cosine theta, sine phi. This is sine theta minus sine theta. You have to do this once from geometry. You have to do this once, and then you can use it without having to do it. But I would recommend you always do this once. Okay. Now finally, what about phi hat? And again, I'll draw the geometry again. X hat, y hat, z hat. Where is phi increasing? Right? Phi is always increasing, and phi hat is always going to be increasing in the xy plane, and it's always going to be something like this. So this is going to be phi hat. So it's on the x hat y hat plane, right? And it's going to always be increasing like that, because this is the direction where phi is increasing. Phi is kind of in the spherical coordinates. Phi goes in a cylinder around the z-axis, right? Circle around the z-axis. So this is z. Phi is always increasing like this, right? So phi has no z component, right? And then of course right, so this is the projection of r hat on the xy, and phi is always going to be 90 degrees with respect to that. Right, so we want to project phi on x. I extend x back here. So this is going to be phi here. So remember, because the projection of r hat, this dotted line is a projection of r hat on the xy plane, because this is always going to be at an angle of phi, phi hat is always going to be an angle of phi, because this projection and phi hat is always going to be 90 degrees apart. So this angle is going to be phi. So the projection on the x hat is going to be in the negative direction, this line here. So it's going to be minus sine phi x hat, and then the projection on y hat is just going to be cosine phi y hat, and then there is no projection on z hat, because phi hat is always going to be perpendicular to z hat. So the last row is going to be just minus sine phi cosine phi 0. So you have to practice the geometry, but you have to do it only once. Notice I did not do this from the notes. I just kind of went back and rederived it. So you should have this capability of doing this at least once. But now you know that the transformation is this. This is n. And the inverse is just n inverse. So n inverse is simply, you could find it, of course, but you could remember that we discovered that the inverse is just the transpose. So I just have to transpose this, take every row and make it a column. So this would be sine theta cosine phi, sine theta sine phi cosine theta. I handled the first row, and then the second row I turned it into a column, cosine theta cosine phi cosine theta sine phi minus sine theta, and then take the last row and turn it into a column, sine phi cosine phi 0. So this is the n transformation, the inverse transformation. This takes me from r hat theta hat phi hat times an inverse to the left to x hat y hat z hat. And now that I have both the n and n inverse transformations, I can transform between, for free now I have the transformation from cylindrical to spherical and vice versa. Let's do now the transformation from cylindrical to spherical. So we said transformation from cylindrical basis to spherical basis is just n m inverse. So now that we've found n and m and consequently n inverse and m inverse, we can find the transformation right away. So the transformation from cylindrical to spherical, right? We start from cylindrical, r hat, phi hat, z hat. The transformation is just n inverse, and we end up with the spherical basis. And then the inverse, which is from spherical to cylindrical. So we start from spherical. The transformation is m n inverse. It's going to be r hat, phi hat, z hat. And from the beauty of linear algebra, we just can directly do this multiplication and find the transformation. So if I do this multiplication, matrix multiplication, I find that n inverse is going to be, so if I take the matrix n, this matrix, and I multiply it by the matrix m inverse, which is this matrix, I get the transformation. So the transformation is going to be, if I do this matrix multiplication, which I hope you know how to do matrix multiplication. If you don't yet, you have to review that. This is something you've studied in the past. So this is going to be sine theta 0 cosine theta 0 minus sine theta 0 1 0. So this is from cylindrical to spherical. Notice the curious thing, the transformation only depends on theta. It does not depend on phi anymore. Why is that? Well, I mean, it makes sense from the symmetry, right? Because right. So ask yourself, why is that? Why does the transformation from cylindrical to spherical seem to be only depending on theta? It does not depend on phi anymore. Okay, so when we go from here to here, the transformation does not depend on phi anymore. It only depends on theta because of the symmetry. So let's discuss that a little bit. Well, it's from the symmetry. I guess we can state it more precisely by noting that so let me draw the XYZ axis. Let's say I have, and then I have my point here. So notice in spherical coordinate bases, in the spherical bases, this is r hat capital, but r small. So this is, let me use green for the cylindrical bases. R small hat is always moves with r hat. So if, let's say, I rotate and I pick this point here, some other point where r hat is pointing in some other direction, right? R small is also going to be following, right? So the relationship between r hat capital and r hat small does not depend on phi clearly. Like phi is the angle of rotation here, right? So it does not depend on phi. So it makes sense that when you go, what does it depend on? So if this is let me draw it from the side, and this is the z-axis. This is theta. So the projection of r hat on r capital, I'm going from cylindrical to spherical, so I want to write r capital in terms of r capital hat in terms of r small hat, right? R capital is going to be what? Is going to be the projection is going to be of r small into r is going to be sine theta in this case. So notice it does not depend on phi because of the symmetry. Phi r hat is always following r as we change phi. So there is no dependent. That's why there is no dependent on phi. And this kind of intuitive non-dependence on phi, we see it right away in the matrix when we calculate it, when we compute it. So because there is no dependence on phi, it's going to be 0 phi hat, right? And again, of course, this is intuitive because between cylindrical and spherical coordinates, they share the same phi hat. So there is really no phi transformation. Dependence on phi, so it's 0 phi hat. And then what about z? This is a cylindrical. This is the z of cylindrical coordinates, z hat. So it's going to be, the projection is going to be cosine theta. So that's where the cosine theta comes in, right? So this is the projection. This is the transformation from cylindrical to spherical. It's this matrix. Now we can find the other matrix, which is n inverse, which gives me the opposite transformation from spherical to cylindrical. I start with spherical bases and I end up with cylindrical bases. And if I do this calculation, this matrix multiplication, I end up with sine theta cosine phi 0, 0, 0, 1, cosine theta minus sine phi 0. Is this the transpose of this? Yes, it is the transpose of this. The transpose property, the property that the inverse is the transpose, still applies. So now we have all transformations of the basis vectors. Right? So if you know at any point in space, if you know the basis vector that are induced by one coordinate system, you can transform to the basis vectors that are induced by another coordinate system. But is that really what we want? We have to ask ourselves the questions. Is that ultimately what we want? Ultimately, why do we use basis vectors? We use basis vectors so we can describe any vector in terms of its scalar components. The reason I use basis vectors is that so I can write A using its scalar components. I can write A as AX, AY, AZ. I want to write A in terms of simply as three numbers. I want to write A in terms of three scalar components. So I want to decompose A as AX, X hat, AY, Y hat, plus AZ, Z hat. That's what I care about really, the scalar components. I really don't care about the basis enough other than providing me the tool to arrive at the scalar components. And those scalar components, as we said, are not unique, are going to vary based on what basis I choose. And again, the bases are not unique. Okay, I can pick, and the bases are not unique because my coordinate system is not unique. I can pick any coordinate system. So really what I care about is how do I transform those. Excuse me, let me stop this to answer the phone. Okay, sorry for the interruption. What were we saying? Okay, what we were saying is that we would like to devise a way, although it's cool that we can now transform between basis vectors, between coordinate induced basis vectors. What we really would like to do is figure out how to transform the components, the scalar components between coordinate bases, between different bases. That's really what we want to do. So if I tell you, hey, if this vector in space has scalar components ax, ay, z, 1, 2, 5, and this is for Cartesian coordinate system. Therefore the bases are Cartesian at every point in space, Cartesian bases. What if I tell you, hey, if I transform to a different coordinate system, spherical, what would the components, how would the components transform? That's an interesting question that we want to answer. And so we know that it will turn out actually that they will transform exactly the same as those basis transformations. And I'll show you why. Okay, and it's an interesting argument. So we said we can write any A, vector A, as a sum of vector components. Those are called vector components. AX x hat is a vector component. AX by itself is a scalar component. Right? We can rewrite this in a clever way. We can rewrite A as what? As a row vector. I'm talking about the linear algebra vectors now, not the directed segment in space vector that we're interested in. Right? So in linear algebra, we can write it as a row. To avoid confusion, I won't say a row vector, I'll just say a row. I can write it as a row times a column. So this is going to be AX, AY, AZ, X hat, Y hat, Z. So to achieve the transformation, I need to transform this, and I need to transform this, right? And here comes, this is still not the clever part. This is just rewriting the same thing here in a different way, in a linear algebra suggestive way. The clever part now is that we can inject the identity matrix in the middle, right? If you have 5 times 4, you can, this is equivalent to 5 times 1 times 4. The identity matrix is the matrix that doesn't change anything, right? So I can write this as AX, AY, AZ times the identity matrix 1 0 0 0 1 0 0 0 1, right? So I can multiply I with this, or I with what comes to the right. It will not change anything, right? I haven't changed anything. I just injected the identity matrix in the middle, right? And you can do this matrix multiplication, and you'll see if you do this multiplication, if you either multiply I matrix here to this to the right, or you multiply it to the left, you'll get the same thing. You'll get the same thing as we have here. So I didn't change a thing. Right? The idea now is that instead of M, I can now apply my transformation. Say I use the M transformation. What does M give me? M goes from Cartesian to cylindrical, right? That's what M does. So if instead of I put something equivalent to I. What's equivalent to I? Well, M inverse M. By the way, it doesn't have to be an inverse M. It could be any matrix and its inverse. It could be N inverse N. Then I'll get another transformation, and so on and so forth. But this is the trick. If I plug in M inverse M, I end up, instead of I end up with AX, AY, AZ, and then I have M inverse, and then M, X, Y, Z. But what is M? M is the transformation from Cartesian bases to cylindrical basis vectors. So this whole thing, M, X, Y, Z, is going to give me R phi Z. So this is going to be equal to AX, AY, AZ, M inverse. Instead of M, X, Y, Z, I'm going to write R phi Z hat. So that's it. This now is how we transform the components, scalar components. So A now is already now written in terms of the cylindrical coordinate bases, R and phi and Z hat. What about the components? What about, right? The components in cylindrical bases, for cylindrical bases, is this. So we say that the scalar components in cylindrical bases is AR, A phi, AZ. Remember, the objective is ultimately to write A instead of AX, AY, AZ as AR, R hat plus A phi, phi hat plus AZ, Z hat. Right? So keep that in mind. Right? So this equals this term here, AX, AY, AZ rho times M inverse. Now I want to keep everything in row column, in a column format rather than a row format. So I just transpose and use the property that if I have A times B and I transpose the whole thing, this equals A transpose B, this equals B transpose A transpose. This is like a linear algebra property. So if I transpose both sides here, I just swap this and this, right? And the transpose of the inverse, we said, for orthonormal bases, M inverse transpose is just going to be M. So if I do that, I get the result that AR, A phi, AZ equals M AX, AY, AZ. So the scalar components transpose in exactly, transform in exactly the same way as the bases from one coordinate system to the other. That's the key result here. That's what you can ultimately do, use the M inverse N and N inverse M matrices for. So the matrices we got for transforming bases can exactly be used, the same matrices can be used for transforming scalar components. So after we're done with homework 1, which is going to be Tuesday probably you're submitted, I'm gonna post homework 2 with a bunch of exercises on those transformations. And if you have any questions, we can go through that too. But yeah, that is the key result. Those transformations that are required to transform the bases, that the coordinate induced bases from one coordinate system to the other, those same transformations can be used to transform the scalar components of the vector. And you'll go through a bunch of exercises in the homework on this. All right, I think that's it in terms of vector algebra, coordinate systems, bases, and all of that. And I think we have enough mathematical maturity now to start discussing vector calculus, which is the other important basis of the mathematical construction of EM theory. All right, see you next lecture, and thank you for listening. Bye.